Alright, hi everyone, welcome to the YouTube channel City of Lections, and in this video we're talking about addition, okay. Adder, which is from our previous video. We talked about the intro to computer architecture, and we said in the last part of the last video we said that the arithmetic and logic unit does two major operations, okay, or does two things, which is addition and the subtraction. Of course, the addition is adder, and then the subtraction is subtractor. So in this video we talk about the addition. How is this carried out? Okay, what does adder mean, and what are the types, and then how is it carried out, and to implement the circuit, the logic circuit for it. So for adder, it is a digital circuit that performs the addition of numbers, or we can say it performs the addition operation. Then the types of adder include the half adder and then the full adder. For the half adder, it is just a digital circuit that implements addition of 2 bits. So let's take an example. When we say addition of 2 bits, let's say 1 1. Let's just leave it at this for our example. Now this is 2 bits. Okay, we're adding 1 and we're adding another. If we are dealing with 3 bits, then we have to add this plus this plus this. Okay, so this will be 3 bits. This for 3 bits and this for 2 bits, right? Now, but the thing is, now we are dealing with half adder, and half adder is the addition of 2 bits. So we'll leave it at this. Okay. Now, when you do this addition, before we talk about the how the logic circuit will look like that we implement this addition, when you do this addition in base 2, of course, 1 plus 1 in base 2 will have 1 0. So 0, and then we'll have a 1 here. And this is just based on the fact that base 2 has 2 numbers. It has 0 and 1. Okay, so here we have 1. Okay, 0 and 1. So here we have, let me just use this one I have here. So here we have 0 and 1. Now when we add 1 to it, there is no other number in front of it, no other number in base 2. So we have to come back to 0. But of course, coming back to 0 just means we add a 1 behind it and we start from 0, just like that. Okay, then that's basically it. So this will be our answer. Okay, we'll have it here. So now, how do we design? Maybe I'll make a different video or you can just watch. There are a lot of videos online that will go deep into addition of numbers in base 2. But this is just the basic process. Okay, it's just the basic process. Knowing that the maximum number of number or symbol, maximum digits or symbol you have for a number is 1 less than the base. So since we're in base 2, we cannot have 2. We can have 1 less than 2 is 1. So in base 2 we have 2 numbers, 0 and 1. So we are saying 1 plus 1. We are already at 1. So if you add 1 to 1, you cannot increase to 2. So you have to go back to 0. But you have to go back to 0, but you keep 1 here. Okay. So yeah, that's that. And that's not supposed to be in this video, but it's okay. So how do we design a circuit that will implement this? The first move is to get the truth table, and we can design our circuit from that. So let's make a truth table of this. Okay, now note that it can be anything here. We can have addition of 1 0. Okay, we can have addition of 0 1. We can have addition of even 0 0. Okay, even 0 0, and of course that will be 0. This will be 1, and this will be 1. Okay, so whichever one. Now let's make a logic circuit for that. I mean a truth table for that. From our truth table, we'll be able to derive the logic circuit of the half adder. So let's go. So we have, let's say, A and B. A, to actually make this closer. A and B. A and B are what we're going to add, which should be 0 and 0 and 0, or 0 1 or 1 0 or 1 1. So these are inputs. These are the inputs. Then of course we have the outputs. Okay. Yes. Now the outputs. Above this line say. So yeah, this will be the output. The lines. Pardon my lines. So for our output, we'll have our answer. Okay, which is the sum, and then we'll have another answer which is the carry. Why do I say this? Looking at this, for this first part of addition here, when we added this, we have to carry 1. Okay, but this is the answer under it, of course. So 0 carry 1, that's kind of it. But for this, just 1, we carried nothing. Nothing was carried. In this case, nothing was also carried, and finally in this case nothing was also carried, so that's 0. So we can say for addition here, I think we've already made the addition. For 0 plus 0, look at it here, 0 plus 0, the answer there is 0, and we carried nothing. Okay, then for 0 plus 1, you can see there. I just want to show us right there. Okay, for 0 plus 1, the answer is 1, and we carried nothing. For 1 plus 0, same thing, the answer is 1, and we carried nothing. Yes, we carried nothing. Then for the last one, 1 plus 1, we had 0 there. The answer is 1, 0 and 1. Okay, I mean 1 and 0 because we have 0 first, but we have this here. I think I should have so we can see it here now. Okay, we can see it here, but the way it's written here is just like the opposite. But we understand that the answer should be here, and then this other part will be here. So maybe I have to switch this switch the table so it will be easy to look at. Let me do that now. Let me switch that so it will be easy to look at. Okay. Alright. Better. So this will just be our carry. No. Should be right. Alright, so this will now be our carry, and this, okay, and this will be our sum. Okay, that looks like 5. This will be our sum. Okay, manageable. So yeah, so now it looks more like what we have here. Okay, it looks more like that. Better. So this is our truth table for it. Okay, this is our truth table for our half adder. So truth table for half adder. Okay, now it's time to get our logic circuit from it. Note that the logic circuit is drawn from logic expressions. Okay, our logic circuit is drawn from logic expression or Boolean expression. Yeah, logic expression. But to derive this logic expression, we use this truth table to draw our logic expression. So what we are doing now to derive the circuits, the logic circuit. With our logic circuit, we need the logic expression. We need logic expression, and as to get logic expression, we need truth table. we need the truth table. So this is just the process we are going through. So now we've started with the truth table, and we've gotten the truth table, and now we start to get the logic expression. Okay, now to get logic expression we need our K-map. Okay, yes, we need our K-map. And now I think I should have added that to, yeah, to get logic, that's in between truth table and that we need the K-map. So for the K-map we just do this. For the K-map we just do this. Now we see that the K-map, we have 2 inputs, so we have 4 boxes based on the fact that we have 2 inputs, and the inputs are A and B. A and B. Okay, so we have A as 0, we have A as 1, we have B as 0, we have B as 1. These are logic circuits. I mean, this the K-map. So look, we have 2 K-map. Why? Because we have 2 outputs. So for the first K-map is, let's say for C, so let me put this here saying K-map for C, or K-map for C. All right. Okay, that's the K-map for C. Okay, now where we want to do the K-map for C. Now look for the place where you have C as 1, where you have 1 as the output, meaning the output is high. Now when you see that, this is the point. Now you look at the input that matches with it. You look at the input that matches with it, and then the input that matches with it, A is 1, B is 1. Okay, so you go to your K-map now, where you see A and 1, where they meet, that's where you put the 1. So look at it here, where you see A as 1 and B as 1. So here A is 1 and here B is 1, and they both meet here. So this is the exact point you put your 1 for C. Okay, so we'll repeat the same thing, but now for the for the S, which is sum. Note that the C means carry and then the S means sum. So let's duplicate this and use it for K-map for S. K-map for S. Alright. But we are not through with A. Okay, we are not through with A. Let me just keep this aside. We are not through with C. Let me keep this aside until we are done with C. So since we have gotten our K-map, now we can derive the Boolean expression from it, the logic expression from it, by doing this. There is a rule. You circle groups of 2. Groups of 2 in the sense that 2 raised to power 0, 2 raised to power 1, 2 raised to power 2, 2 raised to power 3, and so on, just like that. So 2 raised to power 1 is 1, of course. 2 raised to power this is 2, and 2 raised to power this is 4, and so on. Okay, now this is what I mean when I say groups of 2. Where you see 1 in like alone, or 1 in 2 places, or 1 in 4 places, or 1 in 8 places, just like that, you group it. But listen, the rule is this: group the maximum number of 1 you have. So assuming we have another 1 here, we would have grouped them together, but we don't. We just have 1. So what we are going to do, we are going to group this guy just like that, saying this. Okay, now after doing this, then you look what we have here. So in this group you have A as 1 and it is on. So A, and you have B, and that's B when it's on. Okay, other K-map you will see what we'll do when we have another output or 1 being located in another place in the K-map. Okay, but there are videos dedicated to K-map, like there are so many videos online on YouTube you watch and you see K-map. Okay, how to work with K-map. So this simply means C, the Boolean expression or the logic expression for C equals A, B. That's the answer. So this is it. So with this we can draw our logic circuit for C. But note that we are not looking for logic circuit for C alone. The logic circuit for C is part of the logic circuit of the half adder. So this is just C is just one part of the half adder. So to get the other part, we need to complete the other output for the K-map S. K-map for S. So let's complete this. Okay, there should be nothing here for now. We just started S. Okay, so let's complete it. So just like the one for C, the one for S, we also look for the points or the rows where we have S as 1, then go to the inputs. So when we have S as 1, in the inputs we have A as 0, B as 1. So where is A as 0? This is A as 0. Where is B as 1? This is B as 1. So we're going to have here. We're going to have here as 1. Good. Then the next, here we have S as 1. Go to the inputs now that correspond with that. A as 1, B as 0. So here is A as 1, this is A as 1, and this B as 0. So this will be our next. Good, perfect. So again, okay, good. So again, going with the rule where we have to make groups. Now we are going to group this. This is one group, and this is another group. Okay. Now assuming we have 1 here, we would have grouped it like this. Now let me use a different color for that. Assuming we had 1 there, we would have grouped it like this, and not separately. We would have grouped it like this, but they are not like this direction nor this direction to each other. So we are going to group them separately. Okay, to group them separately. But let me just undo this whole thing so that it will be clear here better. So since they are not in that X and Y direction, we group them separately. So this is for B, this is for K-map for S. That means our Boolean expression for S will be S equals, now at this group we have B. Okay, let's go alphabetically. Okay, B for A is 1, which is we have A, and B, but the B is what? 0, so B naught, because the B is 0, so B naught. Okay, since that is done, then we say plus what? Now in this grouping, A is 0, B is 1, so A naught or A bar, then B. Now this thing where you have one part of it, this is kind of the opposite of this, because at this point you have A, at this point you have A bar, at this point you have B bar, at this point you have B. So this kind of expression or this kind of addition, when you add them like this is an exclusive OR. Okay, it's an exclusive OR because it is this or this. Okay, but they are kind of opposites to each other, so you can represent it as A or B, but the OR is an exclusive OR. So that's how it looks like, and it just simply means both if one is on, other one is on. Just like look at the drawing here. I mean, if one is on, then if at least one is on, then the output will be on. That is the definition for the OR operation. If one is on, then the output will be on. But this one is not just OR operation. It is an exclusive OR, which means we cannot have both of them on at the same time. But at least one should be on for us to have on. But if both of them is the same, then it will be off. Okay, so 0 0, that's the same, then we'll have off. Then on, that's the same, then we'll have off. Okay, so but if at least one is on, then they are not the same, then we have on. Okay, on. So yeah, here we have it, or, okay, plus sign showing that it's OR operation, but the circle around it shows that it's an exclusive OR. So that's it. So now for now we have the truth table, we have the logic expression. Now for the logic circuit, what we need is this. This is what we need. I shouldn't do that. This is what we need. This is what we need. Okay, so the inputs we have are A and B, A and B. So we can draw that having this A and B, A and B. Let's look at 13 guy. A and B. Hey, this well, but we understand that's B, okay? So so the next thing will be to draw our circuits then, or logic symbols. So for S, this is the symbol, right? Exclusive OR. So we just give that symbol for exclusive. So many dots. That symbol for exclusive OR. So which is this. Which is this. Good. So A comes here, B comes here. So this is S. Done with that. Then for what? Carry now. Same A and B, but this time A and B is going to what? A and B is going to this. A and B will just AND themselves. So we have it like this. We jump this guy. B come this way. Yeah. Sometimes we call this carry in, okay, or carry out, but let me just leave that for now. Okay. So this is it for half adder. Yeah, this is it for half adder. Okay. So we'll stop here in this video, and then the next video we'll talk about the full adder. It's similar to this, just that it has 3 bits instead of 2 bits. And yeah, so if you have any question, leave it in the comment section, and click on the like button and notification bell to when you subscribe. Of course, subscribe and share, and see you in the next video. Thanks a lot for watching, and bye for now.